summarizing what we've been observing in the last couple of graphs, we have what's called the increasing-decreasing test. So what I kept saying over and over is that if the derivative is positive on a given interval, you notice that the function is increasing on that interval. And if the derivative is negative on an interval, the function is decreasing on that interval. We can do a quick example, and we can try to find the intervals of increasing and decreasing of a given function. Let's work this one out. It says f of x equals x cubed minus 6x squared plus 9x plus 1. Important thing is to take the derivative and see whether it's positive or negative and on which intervals. So I'll first take the derivative. F prime of x is going to be 3x squared minus 12x plus 9. Now to figure out where something is positive or negative, it helps to know where it's equal to 0. That's why we're going to set this function, this derivative function, equal to 0. And if I do some factoring, I'm going to have 3 times the quantity x squared minus 4x plus 3 equals 0. If I factor some more and divide both sides by this 3 here, 3 is just a constant. I can divide by it on both sides. I get x minus 3 times x minus 1 equals 0. So x minus 3 equals 0, or x minus 1 equals 0, x equals 3, or x equals 1. What does that tell me? Well, if I think of a number line, I have that f prime of 1 is equal to 0, and I have f prime of 3 is equal to 0. Those are the only places where the derivative is 0, because we took the derivative, we set it equal to 0, we figured out which x values are going to cause the derivative to be 0. And that's just these 2 points, 1 and 3. Now I can figure out, okay, what's happening to the left of 1? What's happening between 1 and 3? What's happening to the right of 3? That's where we choose test points. So my test point, I'll pick x equals 0 as my test point in the region left of 1. And I'll pick x equals 2 as my test point in the region from 1 to 3. I could have picked 1.7 or square root of 3 or square root of 2. But I pick x equals 2 because it's relatively straightforward. And then I'll pick, let's say, x equals 5 for the region to the right of 3. Okay, so after I get my test points, I plug them into the derivative function over here. So f prime of 0 is 3 times 0 squared minus 12 times 0 plus 9. That ends up being positive. So we have a positive derivative to the left of 1. Next, I'll try f prime of 2. So I'll plug in 2 for x. And what I'll get is 12 minus 24 plus 9, which I believe is going to be negative 3, which is a negative number. So I have a negative derivative between 1 and 3. And then finally, my last test point is 5. I'm going to plug that in. and I will get 75 minus 60 plus 9, which should be 24, which is positive. Remember, if things are going too fast in the video, you can always pause the video and think about a step before you continue. That will help you follow along and stay engaged. Now, how does this answer the question of find the intervals of increasing and decreasing? Well, remember, increasing is when the derivative is positive. So it's increasing on this interval and this interval. It's decreasing when x is between 1 and 3. So our final answer is the function is increasing on negative infinity to 0 union 3 comma infinity. That's reflecting, oh, I'm sorry. It's not 0, it's 1. Negative infinity to 1, which is this part of the number line, union 3 to infinity, which is this part. That's where we figured out the derivatives were positive, which means the function is increasing. The intervals of decreasing are going to be just that one in the middle, the interval from 1 to 3. Let's bring back what we talked about in section 3.1, which is this idea of a critical number and a local maximum and a local minimum. Remember that a local max or a local min could look like a few different ways. Either you have a nice, smooth local minimum, or you have a pointy local minimum. Could be one of these things. These were all local minima. And then you had the local maxima, which looked either like this, or like this, or something like that. Let's read what the first derivative tells us about how to determine a local maximum and a local minimum. We have that c is a critical number of a continuous function f. Critical number means derivative is equal to 0 or the derivative doesn't exist at that point, and that's reflected in these various images. If f prime changes from positive to negative at c, that means f has a local maximum at c. Let's look at these local max images. So in the first part here to the left, the derivative is positive and then the derivative becomes negative. Same thing here, derivative is positive and then derivative is negative. We're not worried about what happens at that special point, at that critical number. We're talking about, is the derivative changing sign at the critical number, going from positive to negative? And in all three of these cases, the derivative is going from positive to negative, and so we have a local maximum. Similarly, if f prime changes from negative to positive at the critical number, then f has a local minimum. So we look at these images. We go from negative derivatives to positive derivatives, negative derivatives to positive derivatives, negative derivatives to positive derivatives. So let's see with an example how we can find local min and local max of this function we just looked at earlier. We already calculated the derivative of this function And again, we want to see where the derivative is changing sign. So we did all that work already. We're not going to do it again. We figured out that the derivative was positive to the left of 1, it was negative between 1 and 3, and it was positive from 3 onward. What that tells us is we have that the function first increases in some way, then it decreases, then it increases again. So remember, if we have an increase to a decrease, that's going to be a local maximum. Increase to decrease, that's going to give us local maximum. If we have decrease to increase, that's going to be local minimum. So what we can say is that f has a local max at x equals 1 and a local min at x equals 3.